This is a review for assigning oxidation numbers as well as an introduction for our reduction and oxidation units. So this part is just going to be a saying for now until we get a little bit further in, but the unit that this is called oxidation and reduction. And so here's what they mean. We use a saying called Leo, the lion, goes gur. All right, and basically it's a saying just to remember the LEO and the GER. Some people use oil rig. I like this one because we will learn another saying later on where we expand on the fact that the lion is a cat, and the sayings just kind of work together to help you remember how to do this stuff. But basically it's LEO, which stands for lose electrons oxidation, and GER, gain electrons reduction. And this is what happens when chemical bonds are formed for the most part, or I should say when bonds that require electrons to be exchanged. So if you remember, not every bond transfers their electron. Some of them share, but we're worried about ones that really exchange electrons for this unit. So both must happen. In other words, in order for one atom to gain an electron, another atom has to lose an electron, which is why you have to have both in a chemical reaction. Also be aware, this tends to throw people off. When you lose electrons, you are actually losing negatives. So if you have a charge of 0 and then you lose a negative, your new charge is going to be +1. Okay, because you're minusing a minus. So if you're going in this direction, it doesn't matter if you go from -5 to -4 or from 0 to +1 or from +1 to +2, you are losing electrons. Gaining electrons does the opposite. If your charge was 0 and you gained an electron, well, your new charge is going to be -1. So if you're going in the left direction, you are gaining electrons. So that's just a quick review or an introduction to what we're going to be doing, and then the rest of today is going to be spent on just reviewing the oxidation numbers, which hopefully you should be pretty good at by now. So assigning oxidation numbers, we have our rules. There's 6 of them. When elements are alone, we call them free elements, they're 0. So if you just see Na, it's 0. Cl2, 0. S8, 0. You get the idea. These are not in compounds, they're always going to be 0. A common mistake is to think that Na is +1 because the group 1 rule that says that group 1 is +1 and Na happens to be in group 1. But here's the issue. When Na is in a compound, yes, that's true, but if Na were alone, then it's an element and it would be 0. So just be aware of that. So group 1 +1, group 2 +2, F, H, and O respectively. And then the rule that we follow is that the individual charges have to add up to equal the total charge of the compound. Whether that charge is 0 or whether that charge is negative or positive, it does not matter. It always has to equal the total. So looking at this first line of problems, since they have no charge in the top right-hand corner, we are going to set them all equal to 0. And then we apply our rules. It's pretty simple. There's a rule for O, it's -2. There's a rule for Na, it's +1. -1, -2, 0, and 0. So these last two were tricks. F does have a rule, but that's only when it's in a compound. When it's alone, it has to be 0 because that's the only way it could equal 0, because 0 times 2 is 0. Same goes for S. And then these three, those are the rules. And now what we do is we multiply down. So I have 3 -2s, I get -6. 2 -1s, I get -2. And 4 -2s, I get -8. 2 +1s, +1. So I multiply down to figure out my total charge from each individual element. Now I do the math to make it equal 0. S is going to have to total plus, oh, made a mistake here. That should be +2. S is going to have to total +6, so I can have +2 + 6 be 8, and 8 - 8 equals 0. Therefore, since there is only one S in the entire equation, it gets the whole +6. If there were 2 S's, it would get +3 each. If there were 3 S's, they would get +2 each. You should get the idea at this point. Here I'm going to need +2, since there's only one Fe, it gets the whole +2. Here I'm going to need +6 to make this 0, since there's 2 aluminums, they get +3 each, and then those two are done. So that's how you do it if you're setting the charges equal to 0. In the next round, we set the charges equal to the total charge. In this case, the total charge isn't 0. It's going to be +1, -2, -2, and -3. So assign our rules. So I have two -2's here. This -2 that's written in is for the whole charge. That's here. I'm trying to squeeze in another -2 for the O. It's a little bit easier here. Okay, we multiply down to get all of the total charges. So that's what I can figure out. And now I need to figure out the other elements in order to make the whole thing equal 0. So in this case, it's got to be -4. Since there's only one n, it gets the whole, should be -4. Okay. In this case, I'm going to need +6. Since there's one of them, it gets the whole +6. Here, I'm going to need +12. Since there's two of them, they are +6 again. And for this one, I'm going to need +5, and there's one of them, so it gets the whole +5. So that's how you do ones with charges. Now, these next two are two-step problems, and there's a reason. They are equal to 0. We have a rule for oxygen in this case, or in both cases, but we don't have a rule for P and we don't have a rule for Cu. So there's two ways of doing this, okay? I'm going to do one way and one the other way. So the one way of doing it is to look up NO3 separately. So if I go to table E in the reference table and I look up NO3, it has a charge on its own of -1. So oxygen is still -2, it's a rule, but now I set it equal to -1. So what I would do is multiply down, I get -6. That means N has to be +5. And then I can take that +5 and transfer it here and then solve for aluminum. So the way I would do that is there are 9 oxygen in total because this distributes. So I'm going to get -18. There are 3 N because that distributes. So I'm going to get +15. And then mathematically, Al has to be +3 to make the whole thing equal 0. It doesn't get multiplied by 3 because Al is not in the parentheses. That's one way. I actually think that might be the longer way to do it, but it does break it down to really show true understanding. The other way of doing it is PO4. Is you look at PO4 as a polyatomic ion, and PO4 from table E has a -3 charge as a unit. So if we think about PO4 as having a -3, there's 2 of them, that would give me -6. Okay, so I guess I'll put it up here. If PO4 as a unit was -3, then my 2 PO4s would give me -6, which means my Cu is going to have to give me +6, which means they are +2 each. That's the true way to get it equal to 0. So once you know that, I can go back and put the +2 here, and then solve for the P individually. There is 8 oxygen, I get -16. There's +6 from the copper, which means I'm going to need +10 from P, which will give me +5 each. So both methods work. I don't care how you do it, but I will tell you that for naming purposes, if I just need to know the oxidation state of copper because all I want is a name, then this method up here is a much faster way to arrive at that. Whereas if I'm doing oxidation states, sometimes I may actually need to know the N, like in this problem, and then this method might be the better option. So it really depends on what you're doing. And now the last two, very simple. There is a exception to the rule. The reason you know there's an exception, these would be equal 0, is the rules don't add up. An example would be the rule for H is +1, the rule for O is -2. If I multiply down, I'll get +2 and -4, and that won't equal 0. So what we do is we erase one of the rules. In other words, these rule lists are also in order of priority. This is the most important, this would be the least important. Since the rule for H is more important than the rule for O, then the rule for O goes away. And now we can make O anything we need in order to make this true. So to make this true, I need to make O -1, so I get -2. The same thing with OF2. O would be -2, f is -1, so -2 does not equal 0. So what I have to do is, since the rule for f is more important, I ignore oxygen's rule. Oxygen is going to have to be +2, which will make the whole thing +2 and make it equal to 0. So the way you know you're dealing with an exception, the math does not add up, and then you break whichever rule happens to be lower and then put in any number needed to make the math correct. Now the practice for this is going to be on the back page. The back page has an entire set of practice problems. I will send out an answer key on this eventually, so you can check your work, and obviously there will be a Castle Learning, which is what gets graded.